we're going to explore one of the most mind-bending concepts in physics: time travel. From Einstein's theory of relativity to the latest scientific discoveries, we'll delve into the possibilities and paradoxes of traversing the timeline. Buckle up and join me on this journey through time. What is time travel? Time travel, in its simplest form, is the idea of moving through time, either forward or backward, to a different point in the past or future. It's a concept that has fascinated humans for centuries and has been explored in countless science fiction stories, films, and books. But what does it really mean to travel through time? At its core, time travel involves manipulating one's position in the timeline, allowing a person or object to experience a different moment in history. This can be thought of as a journey through the fourth dimension, where time is the additional dimension, beyond the three spatial dimensions we're familiar with. Time travel can be thought of in two main ways: moving through time in a linear fashion, like a car on a road, or moving through time in a non-linear fashion, like a jump from one point to another. The linear approach would involve traveling at incredible speeds, or using a vehicle that can withstand the stresses of time dilation, while the non-linear approach would involve using a device or phenomenon that can create a shortcut through spacetime. Despite the many depictions of time travel in popular culture, it's essential to note that time travel, in the sense of moving through time in a non-linear fashion, is still purely theoretical. However, some scientific concepts, such as wormholes and quantum entanglement, suggest that time travel could be possible under certain conditions. As we explore the science behind time travel, we'll delve deeper into these ideas and the possibilities they present. The science behind time travel. The science behind time travel is rooted in our understanding of spacetime, which is the fabric that combines space and time. According to Albert Einstein's theory of relativity, spacetime is not fixed, but rather it's dynamic and can be affected by gravity and motion. This means that time is not absolute, but rather it's relative and can be influenced by the observer's frame of reference. One of the key concepts in time travel is time dilation, which occurs when an object approaches the speed of light, or is placed in a strong gravitational field. This causes time to slow down relative to a stationary observer, a phenomenon that has been experimentally confirmed in particle accelerators and GPS technology. Wormholes, on the other hand, are hypothetical shortcuts through spacetime that could potentially connect to distant points in space and time, allowing for faster-than-light travel and potentially time travel. Quantum mechanics also plays a role in time travel, particularly in the concept of quantum entanglement, where particles become connected and can affect each other even when separated by vast distances. Some theories suggest that entanglement could be used to send information through time, effectively allowing for communication with the past or future. Additionally, some models of quantum gravity, such as string theory and loop quantum gravity, propose the existence of extra dimensions and parallel universes, which could potentially be used for time travel. While these scientific concepts provide a foundation for understanding time travel, it's essential to note that the technical challenges and paradoxes associated with time travel remain significant. However, by exploring the science behind time travel, we can gain a deeper understanding of the possibilities and limitations of traversing the timeline. Time travel paradoxes. Time travel paradoxes arise when the consequences of time travel create logical inconsistencies or contradictions. One of the most well-known paradoxes is the grandfather paradox, which suggests that if a time traveler goes back in time and kills their own grandfather before he has children, then the time traveler would never have been born. But if the time traveler was never born, who killed the grandfather? Another paradox is the bootstrap paradox, where an object or information is sent back in time and it has no clear origin. For example, if a time traveler goes back in time and gives a younger version of themselves some information or object that they already possess, then where did it originally come from? This creates a loop where the object or information has no clear starting point. The predestination paradox suggests that every event in history is predetermined and cannot be changed. If a time traveler tries to alter the past, they will either fail or their actions will be part of the events that led to the present they came from. This raises questions about free will and the ability to change the course of history. The multiple timelines paradox proposes that every time a time traveler makes a change to the past, they create a new timeline or reality, rather than altering the existing one. This would result in an infinite number of parallel universes, each with their own version of history. Time travel paradoxes highlight the potential problems and inconsistencies that can arise when trying to manipulate time. They challenge our understanding of causality, free will, and the nature of time itself, and encourage us to think more deeply about the consequences of time travel. Real-life time travel experiments. While time travel remains purely theoretical, scientists have conducted experiments that manipulate time in fascinating ways. One such experiment is the Hafele-Keating experiment, where atomic clocks were flown around the Earth on commercial airliners. When compared to identical clocks on the ground, the flying clocks showed a slight delay, confirming Einstein's prediction of time dilation due to motion. Another experiment is the gravity probe, where a clock was launched into space and compared to a clock on Earth. The results showed that time passes slower in stronger gravitational fields, as predicted by general relativity. This effect, known as gravitational time dilation, has also been observed in GPS satellites, which must be adjusted to account for time dilation caused by their high-speed motion and altitude. Quantum entanglement experiments have also demonstrated time-related phenomena. In delayed choice quantum eraser experiments, particles can be entangled and then separated, with the state of one particle affecting the other even when measured at different times. This raises questions about the role of time in quantum mechanics and the potential for quantum-based time travel. Additionally, scientists have explored the concept of time dilation using particle accelerators. By accelerating particles to near-light speeds, researchers have observed time dilation effects, confirming the predictions of special relativity. These experiments have pushed our understanding of time and its relationship to motion and gravity. While these experiments don't enable human time travel, they demonstrate the strange and fascinating effects of time manipulation. By exploring the boundaries of time, scientists continue to refine our understanding of the universe and the laws of physics that govern it. Thanks for joining me on this journey through time. While time travel remains purely theoretical for now, exploring its possibilities and paradoxes has led to groundbreaking scientific discoveries. Who knows what the future of time travel holds? Subscribe to our channel for more mind-bending content.